Hello, everybody. Thanks for joining us today. You're part of the 300 people worldwide who have registered to this webcast. This webcast, powered by iMicronews, will present the advanced RF SIP for cell phones market. Let me quickly introduce your group of companies. We provide marketing technologies and strategy, media and corporate finance services, reverse engineering and reverse costing services, as well as IP and patent analysis. My name is David Jordan. I'm part of the sales and coordination service from your development. Before starting the presentation, let me give you some practical information. You have the possibility during all the webcasts to submit questions. To do so, you simply have to use the box at the bottom of the screen. It is labeled Ask a Question. We will answer as many questions today as time allows. And for remaining questions, we will follow up with you via email. Concerning the materials and contents of the presentation, please note that they are already available and downloadable in the resources section of the webcast platform. Furthermore, within 24 hours, you will receive also an email after the webcast with the link to the recorded session. Today, your development will share their analysis on the advanced RF SIP for cell phone markets. We are pleased to welcome Santosh Kumar, Principal Analyst and Director Packaging, Assembly and Substrate from Seoul, Korea. Santosh, the floor is yours.
Yeah, thank you, David, for the introduction. So today the webcast is about the advanced RF system in package for the mobile application. So I will, I will talk about the trends in the RF for the mobile, and then go into the packaging. And the aim of this webinar is mainly to discuss about, what are the package trends for the RF SIP, different kind of modules in the mobile, and then also talk about the ecosystem, supply chain and ecosystem. Okay. So if you see the cellular technology development, so it's, from 2G to 5G, it's, like less than a 3-decade journey. And so it started at around, like 1992, and on an average, if you see between the two, like the technology generation, like from the 2G to 3G and 3G to 4G and 4G to 5G, on an average, it will take around, like the 10 years. Of course, like between the two, like between 3G and 4G, or between the 2G and 3G, there are some intermediate technology. It's, like update of the previous generation technologies. And in terms of the data rate, if you see for the 5G, it's, like if you see theoretically possible data rate, it's really going to, like in the gigabits per second, like for the 5G going to around 20 Gbps. But in the reality, in the real life situation, we will not achieve so much, but still it will be more than the in the gigabits per second range. For the 5G, if you see the spectrum defined by the 3GPP, so it's the two. They have divided into two segments. It's the sub 6 gigahertz segment, and it's also called, like the 5G NR FR1 band. And in this band, we have, the N77 band and N78 and N79 band. And this band is called the sub 6 gigahertz. So it's, less than the 6 gigahertz frequency. So in terms of, the implementation, so initially the Korea and Japan, they are, the main user of this, also called the ultra high band LTE spectrum. And then it will, like expand into the Europe, China, Russia, and rest of the world. And already, like the first product supporting these bands, these are in the production. And the second, the band is a millimeter wave spectrum, and that is, like many people are saying that is, the real 5G, we can say, because here we have, the frequency is more than the 24 gigahertz, and it's in the range of 24 to 50 gigahertz. And in here, like also there are different bands, like N257 band, 258 band, and 260 band. And so band N27, that is the main band for the 5G millimeter wave rollout in the US, Korea, and Japan. And for the rest of the world, it will be the band N258. Mainly, it will come next year. And the first millimeter wave antenna module, they will support this 257, 261, and later they will support the 260 band. In terms of the application, so you can see, like there are, based on the frequency band defined, there are the different use cases of this 5G. So basically, we can divide it into, like the three group. One is we called the sub 1 gigahertz, that is mainly for the IoT applications. And then we have the sub 6 gigahertz where we have, like the mobile, and also we have the different application supporting the autonomous vehicle and video teleconferencing, smart grid, connected wearables, different thing. And then if we go to, like the millimeter wave, more than 24 gigahertz, then we have, like the robotic service and advanced AI assistant, autonomous vehicle, and cloud computing, and a lot of different things. And one of, the key selling point of this 5G, especially for the mobile, is the very high quality video and real-time application, AR, VR time application. So the high quality video, they are driving the demand for this increased bandwidth and the peak data rates, and new applications such as the AR and hologram, they're expected to push the data rate demand. So if you see currently we are, like we can say at the 4G advanced stage, and we can say with the rollout of the different phone, so we can say we are at the 4G advanced, and pre 5G sub 6 gigahertz range will be there. If we see the RF content in the mobile, so in every cellular generation, like it all leads to the new technology and the additional RF content. So if you start from, like from the GSM to the HSPA, so we have the diversity, module integration. And if we go to the LTE, then we have the Wi-Fi and 2x2 MIMO and the carrier integration aggregation, and some more high band come into it. And then we further go to LTE, then there will be more, like carrier components available for the carrier aggregation and introduction of the ultra high band. And then for LTE Pro, we have the introduction of this 4x4 MIMO. And for this 5G sub gigahertz, we will have the dual connectivity where we have, like at the same time our, like the user equipment, like for example, mobile, they are connected at the same time to the 5G network and also the 4G LTE network, so that, to take the advantage of both the air standards at the same time. And this dual connectivity, and also there will be, the band refarming, especially, like some of the bands from the, low end and the mid high band that will be, reallocated from the 5G sub 6 gigahertz. They will further expand, the RF content in the mobile. Okay. If we see in the smartphone, the basic modules in the smartphone, so we have, like the display modules, we have the sensor modules, and we have the connectivity modules and the RF modules. And so in the RF modules, we can say, like you can see we have from the modem to the antenna, and between it there are a lot of the different components, the transceiver, front-end modules, power amplifiers, and different kind of the filters. And then we have this connectivity module, and that also we can say is a part of the RF module in there, where we have also the Wi-Fi front-end module and Wi-Fi Bluetooth combined, and also the NFC controller module. In terms of the system of package found in the different smartphone components, so you can see, the red color is the the components which are in the system in package, and the other, the gray color that is not in the system in package. So if you see, especially you find, towards the left-hand side, where you can find, the numerous system in package, and they are mainly supporting these RF components in the mobile. And if we see the main RF front-end component, so if we can, define this RF front-end component, so it's, like the set of the different technology and components, and mainly situated between, the modem and the antenna, and they are, responsible for physically transmitting the receiving information over the air, and also due to the need to implement higher number of bands and increasing, the quantity of circuitry, even the smaller areas. So that's why, the system in package format, it has become, the natural progression for packaging these front end. So you can see, the different path, like the basic receiver path and the transmit path. And the components, include the various kind of switches, filters, amplifiers, and antenna themselves. And so, inside, this the front-end modules, there are different kind of, the RF front-end modules in the mobile. So if we see the cellular, so we have, the highly integrated PAMID, the power amplifier module with integrated duplexers. And then we have, the PAD, which we can say the power amplifier duplexer modules, where we have the power amplifier and integrated with the duplexer. For the PAMID, we have the power amplifier, low noise amplifier, switches, different kind of the IPDs, they are and filters, and they are all integrated in there. And then we have also the receive diversity module, and then we have the antenna switch module, also called the switch plexers. Then we have the antenna plexers or multiplexers, and then we have the low noise amplifier multiplexer modules. Also we have the multi-board multi-band power amplifier. Sometimes it is they are in the discrete, but sometimes they are available with, integrated, even though it's the single die, but integrated with a lot of the different passives. So we have counted it into the system in package format. And for the connectivity, we have the Wi-Fi and the front-end module and the WIGIG front-end module. So if we see, the kind of the architecture for the RF front-end module, especially for this PAMID. So here you can say, it can include the power amplifier or load plus low noise amplifier, filter, switches, and the antenna tuners. And if we see the RF connectivity implementation by the phone segment, so if we see the value mid-end and low-end phone versus the premium phone, so they have, the different kind of the RF implementation in there. So for the standard smartphone, we have, in general, we have the two LAN front-end modules, FAMID, and multi-mode, multi-band power amplifier for low and mid-band, a diversity module for MIMO 2x2, and the high-band power amplifier integrated with the duplexer PMID module. For the high-end smartphones and the luxury premium phones, so already the MIMO 4x4 is implemented. So it leads to more diversity module and enabling use of the 5G NR bands for the downloop. Also, we have the low band, mid band, and the high band PMID that will ensure the uplink improvement through more and more the carrier aggregation. So if we see in terms of the evaluation of the mobile broadband RF front end evaluation, so if you see in 2017, if we see, so we have
the different band, different low band module, so it's less than 1.5 gigahertz module. Then we have the mid band, so it's between 1.5 to 2, and then above that we have the high band module between the 2 and the 3. And then what happened in 2018, there are some more band included in the low band module, so we have more filters coming in there. And then also this high band and the mid band,
they, they are integrated. And then there is more, for the ultra high band greater than the 3 gigahertz come into this, implemented in it. For this year, for 2019, with the coming of the 5G, especially the 5G sub-6 gigahertz, we will see there will be more, band refarming for the low band module, and also band refarming for the, as I already mentioned, for the this high band plus mid band module. There will be more carrier aggregation. And in the ultra high band module, so the new radio, the band which support the dual conductivity, especially you can see this 5G sub-6 gigahertz. So they will be integrated with this UHB module. And then we will see, for some of the very few devices, the appearance of the millimeter wave modules. And if we go to, more than further 2020, then we can say, this millimeter wave module is a separate module. And for this more than 24 gigahertz application, and then we have the low band and the ultra high band module, and high band and the mid band module together. So it's you can see it's kind of the 4 module over there. If, for example, if we see, the iPhone X simplified structure, so what is happening, even though, for the iPhone X, even though there is, the increase in the size of this phone, it's like 5.88, but in terms of the RF component, there are, the size decreases, because, you have the bigger battery and you have the new functionalities such as, the facial recognition ID. So what happened for this RF, so the different, RF components in this RF board. So the size, it shrunk to, around 320 millimeter square, and for the connectivity, it shrunk to, around 160 millimeter square. So there is, the trend, even though, the smartphone size is relatively increasing compared to before, but because of the integration of the different functionality, also because of the bezel-less. And so there is, the more and more, the area available for this RF module, and that is very big challenging, especially with the introduction of the 5G in the mobile. So if we see, the structure of this 5G impact on this RF front end, so you can see here, so we will see, it is becoming, very, very complex with the integration of the new technology like carrier aggregation, MIMO, and dual connectivity. And so we will see, for this Wi-Fi Bluetooth module antenna 2x2 MIMO antenna, it will be maybe shared with the diversity receive module. And then for this power amplifier module, you can say that you can see, as I shown in the previous slide, like this 5G PAM will be implemented over there. And then separately, we have this millimeter wave antenna in package connected to the separate millimeter wave baseband modem. So we need, the separate modem for this 5G. And here in this antenna is integrated along with the transceiver IC, and maybe with the different kind of the front-end components, separate components. So if we see, the kind of, the 5G trend for the mobile handset, so it's in a kind of the additional RF interface. So initially, in terms of the usage of the cellular infrastructure, so 5G phone, they will still use the former, 4G frequencies to their, the fullest extent. And in addition to those frequencies, the industry, they will look towards the millimeter wave in order to increase the throughput. And from the technological point of view, millimeter wave oriented RF component should not be able to work with the standard sub-6 gigahertz component, so it will be separate. And it, it's someone can expect that this, if we add this, the millimeter wave to the standard handset, so it will not be the different, for example, like the addition of the new band, which involves, the creating the new series of the new RF path with dedicated power amplifier. But actually in the practice, it's likely to be different. So the trend is towards the higher integration for the LTE, And much work is also being done towards, the monolithic integration of all components into the standardized chips, and it will come later. And also we will see that, the standard LTE RF front-end module, they will eventually in more and more integrated into CMOS compatible technologies with more components. But with the issue with the millimeter wave is that the current CMOS compatible technologies, it cannot offer the expected performance at very high frequency. And so we will see, the gallium nitride based substrate, they will be, like more and more being looked for this power amplifier to support the millimeter wave. And so integrating it in the, the existing module, which will be, for this millimeter wave will be difficult. And also this 5G millimeter wave, it's expected to implement the disruptive technologies like massive MIMO at reception. And so those innovations are, like fit for the millimeter wave band, but do not apply much to the sub-6 gigahertz frequency. So we expect that, there will be creation of the additional modules in the phone, which is dedicated only to the millimeter wave in there. And on the other hand, we will show that, like the RF front end as designated for, 4G, it will continue to evolve in the same direction with additional bands, with additional carrier integration, carrier aggregation, with additional antennas, but more and more integration. If we go to the advanced packaging platform, so these advanced, like a platform at the YOL, we have, classified it at the different level. So at the vapor level, we will have, the fan in, fan out, and the 3D TSV based technology. Where interconnect can be the TSV or through glass via, or it can be bump or pillar, or it can be the silicon or the glass bridge. Then at the substrate level or strip level, it's also, kind of the panel based. So it can be flip chip based in terms of interconnect, or it will be the wire bond. And in terms of the package, it will be the standard organic substrate packaged or the advanced organic substrate, where we have the 2.1D and 2.5D or also embedded package. And the substrate material can be the ceramic, lead frame, and the others. And then if we go more one level below, the packaging, so it's, like the flip chip BGA, CSP, or LGA, or the wire bond LGA, BGA. And then in terms of the module, we have the system in package or package and package module. And in right side, we have the panel level, where the panel size is, like more than the 300 into 300 millimeter squares, like fan out PLP at the die level. Interconnection can be RDL, and substrate is the organic or the glass substrate, and another separate is at the second level is the embedded die in the laminate or in the flex and the PCB. So if we see this SIP, so it's, like basically we can divide it into two parts. One is, like the substrate based SIP, and another is the vapor level based SIP. So in the vapor level based SIP, we have the fan out panel level packaging and fan out vapor level packaging, and in substrate based, we have this, the flip chip based, wire bond based the packaging. And so the system in package, they can leverage the assembly and packaging technology and IC assembly and packaging, plus also the SMT technologies, and which we see at the EMS level in the supply chain. So the IC and packaging technology, as I mentioned, is, the RDL, bumping, copper pillar, substrate, TSV, wire bond. And then the SMT technology is the paste printing, SMD, passive, pick and place, especially the high speed chip shooters, etc. So if we see, like the inside RF system in package, and this is the example of this Avago FEM8072. So this is the mid-high band integrated PAMID module. So here we can see, like there are, a lot of different filters, and it's, like more than, the 10, 12 filters. We have switches, we have the passives, we have the power amplifiers, and low noise amplifiers. So here we can see the power amplifiers are still in the wire bonded, and then all others are, in the case of like filters and the switches, They are a kind of the WLP package, wafer level package. It may be the solder ball, or maybe the copper pillar interconnect in there. In the right side, we can see the RX diversity module. So here we have the filters and switches and low noise amplifier. So in terms of the integration, this SIP, they will, reach really very high level of integration and accommodate the various heterogeneous technologies from 3-4 compound semiconductor to the silicon ICs, and also they can use, the MEMS technology for the resonators and switches from there. So in terms of the RF front-end segmentation, so this is, the module integration and multiplication, plus we have, the different RF signal multiplexing. There are the main evaluation. If you see the area distribution per function, so we have this PAMID that is, really taking the big area at the high end phone. And at the low end phone, we have this power amplifier module. And also, we see the multiplexers. They have now, entered the market with quad and the quinflexers, also following carrier aggregation and the MIMO 4x4 over there. So total area, you can see the if you go from, the mid-end phone to the high-end phone, we can see, the total area is for this RF board is decreasing there. Okay, the power amplifier module densification. So here you can see, the suppliers, they are moving towards more and more highly integrated solution with enhanced AMI and integrated antenna matching IC. So this is, as I said before, so here we have, in the left side, this is the mid-band module and the high-band module. So if you can see that for the mid-band, the area is the 21 millimeter square, and the high-band is 45 millimeter square. And so it is, now integrated in this high mid-band module. So we have, compared to, the mid-band and the low band, we have the increase in the area 85 millimeter square, but we have the decrease in the number of the IOs and more, integration and more filters and the different kind of interconnect in there. And in terms of the requirement for this RF system in package for the 5G in mobile, so we can see, the different trends. So as I mentioned, it is the integration of more and more components in the package. So we have more active components, more passive components. And so it also, at the component level also, there is the trend of reduction in the size. And also maybe we'll see that multiple, the dies, they will be integrated in the SoC, because it's really, becoming very, very difficult to integrate all those different components within the limited area where you have also, when you implement this 5G millimeter wave, you need the multiple, antenna in package, at least 3 antenna in package in there. And also the filters, their form factors maybe, decrease during the TSV, for example, stacked filters. And so there is, the scaling area scaling at both the XY and also the G height, So we see the smaller component spacing, so higher accuracy and high speed pick and place equipment is required. We will also see, some change in the this EMC molding, maybe with the small filler size, so that, they can be applied for these small components. And we see the small size shape and also the double size BGA, molded BGA. So to, to save the area. So already it has been implemented where we have in the BGA both side, the different components and active both as passive. We will see the more fine line space features for the substrate. And also we see the ultra thin substrate with maybe lesser layers, which will be supported by the fine line space features and having the same integration capability. And other is, for the same SIP height, we will see the use of the thicker passives, which will have the better performance. And for the molding, also we will see that it will currently, it's mainly the transfer molding is used. We will see that it may the trend is towards moving to the compression molding because of it will have the compression molding has the advantage of the low pressure molding, and it will prevent the damage of the components and the cracks in the ultra thin substrate. And also it has, in terms of the tool cost and the material cost. So in terms of cost of ownership, the compression molding has less cost of the ownership. Also, there is less material loss, and it is also, widely available at the different OSATs. And in terms of the shielding, where we see the trend towards, the conformal shielding and highly conductive and laser marking visibility. And it should have adhesion to the package mold and the side wall coverage and low resistance to the ground. And in terms of, if we see in terms of the cost and the time to market reduction, so, as I mentioned, if you see the SIP, so it's either, the substrate-based SIP or the vapor level based SIP. So currently it's all, these front-end modules, RF SIP, they are, based on the substrate-based SIP, and mainly coreless substrate is used. So for the fan-out, yeah, it offers, the better electrical, RF, and thermal performance, and it fulfills the low G-height requirement. And it's also, currently available at, the different OSATs, but compared to, the flip chip, it's costly, and there is also the package size limitation. Because of, if the package size is big, then there is some reliability issue. And it has, the long lead time related to the laminate-based solution. So currently, it will still be, I see this substrate-based SIP, that will be the main solution. And in the due time, maybe we will see, if the cost go down and and it will become, especially if this fan out is able to integrate the both side, like it can support the double side RDL layer, then we will see the more and more implementation. So currently, if you see some of the companies, like for example the Samsung, the Samco, they have implemented this, the both side RDL for their Samsung Galaxy Watch. That kind of package is very good, to support this RF SIP, especially in terms of, like a lot of the increase in the components. And so it will save your area and also have the tighter integration with fine line space features. If we see the technology toolbox for RF SIP for 5G mobile, so it's, as I already mentioned, so it will have the dual side assembly, and so dual side mold package, and we will see the mode maybe embedded active and passives. And in terms of shielding, it will be both conformal and the compartmental shielding, and the substrate will be thin, and it will be the passive component. It will be, the more small size. The millimeter wave, the antenna will be integrated inside the package. And low loss material will be needed for the high frequency to prevent the high frequency signal loss for the high frequency signal propagation. And in the terms of the molding, we will see more trend towards the compression molding over there. So if we see this, the package trend for this front-end module, the package evaluation. So you can see, if we go to before, like 2008, where we have only two GSMs. So at that time, there will be no front-end module. There will be mainly the discrete power amplifier and using the lead frame-based solution. And the antenna is, outside the body. And so with this 3G, we see, the one FEM will be used for this transmit and receive, and then discrete was still the main, the power amplifier, and for this the 4G LTE we have on an average 3 to 5, the front end modules, and the power amplifier and the front end module they have integrated, but that is still the single side SIP over there, and antenna also have evolved from the phone case and it go to the flex PCB. And then as we enter into this 5G space, so at first it will be the sub 6 gigahertz. Here we will see, the more double-side SIP will be there, and in terms of the number of modules, it will be the 5 to 7 front-end modules, and there will be this power amplifier and the FEM integration. And in terms of like the bill of materials for the packaging, so 5G sub 6 gigahertz, we can say it's a kind of incremental a need. It's not very like drastic change in the bill of materials. Still the substrate which is currently used for the 4G LTE, that will be the use that can serve the purpose. No need to go to like ultra low loss dielectrics. But for this 5G millimeter wave, that needs a disruptive innovation in the packaging. So we will see the enhanced double-side SIP antenna that will integrate inside the package. Since for this 5G millimeter wave, so like the loss in the signal is very high because of the short wavelength. So we will see the antenna coming more and more closer to the transceiver IC, RFIC, and also since for this millimeter wave the antenna size becomes small, so it can be like integrated inside the package. So in terms of the substrate, we will see the organic, also maybe ceramic coming into it, and package will be mostly 5G flip chip, and introduction of the new material, low loss dielectric mold etc, and then EMI shielding, different kind of conformal, both compartmental. And also we will see because like for this 5G millimeter wave module, so power dissipation is big issue in there. Thermal is big issue. So maybe we'll see the RFIC, this power management IC may be integrated inside the module. And if we go like more further like high end of this 5G, then we will see the coming of maybe the fan out vapor level packaging or PLP, and antenna may be integrated in the thin film RDL, and we will see the introduction of the glass substrate, and more like high grade of the low loss and the electric mold etc materials, and the new kind of shielding technology may be sputting film. And in terms of the integration, maybe we will see the modem integrated with the power amplifier, antenna, RFIC, and the front end module. So if we see this assembly and the packaging market for RF for the mobile, so we can divide the packaging of these RF components at the two level. One is at the vapor level and other is at the SIP level. So at the vapor level, that is prior to the SIP assembly. So we have like the different components like the filter, switches, and power amplifiers, and different components. So they are like for example filter. So they are for the SIP assemblers, like for the SR. So they are available as the SMT components. But at the vapor level, you need to do like the cap vapor bonding or the TSV packaging, or maybe the RDL and UBM or bumping and dicing. And also the components, they are also available as the bare die in the wafer form. And so they are mainly use the wire bonded process. But there also you need to do the vapor grinding, dicing, and the testing and inspection in there. So that is also a part of the packaging market. And then further we have like at the SIP level, we have the SMT wire bond molding, shielding, and VGA, LGA, and the test. So if we see the total assembly packaging market for this RF SIP in the mobile, so if you see the vapor level packaging, so that will be around 9% of the total packaging market in 2018 was 3.3 billion USD, and 9% will be around the WLP, and mainly 91% will be the SIP. Same trend, like we'll see it will continue, but the total packaging market will grow at 11% CAGR to reach to like $5.3 billion market. And in terms of the different kind of the front end modules I mentioned over there, so PMID will have in 2018 it has the around 23% market share over share, and that share will continue to increase over there, and we believe that in 2023 it will go to around like 40% market share will be there. Then we have like the PM or PAD module. that we will see, like more, the decrease, and it will be more and more going towards this PMID. And receive diversity module, that share will increase, and so it will be, like increase to around 15%, and because of this more and more, the carrier aggregation. And in terms of, and for this Wi-Fi will also increase. And in terms of the WIGIG FEM, we don't see much implementation of the WIGIG front-end module in the mobile, maybe at, like the mid-end phone, but it's not so much, like integrated in the mobile. Maybe we'll see more and more at, like for the gaming and all the consumer, like the home application in there. And millimeter wave module, front-end module, it will currently, last year it was, there is no any market in there, but it will grow to around, like 4% by 2023. And if we see the evolution of the antenna in the smartphone, so antenna is, it was outside the smartphone body, and then it like come to the case, and with the 4G it went on the flex, and then for the 5G, especially for a millimeter wave, it's integrated in the package. And as I mentioned, for the millimeter wave frequency long path from the semiconductor package to the antenna, it results in the higher losses, making it desirable to integrate the antenna as well into the system and package. And also high frequency, it requires the smaller antennas, which from a footprint point of view, it would be easier to integrate into the SIP. Currently, however, like a single antenna, it need to work with, the number of the different frequency bands with the multiplexers and the antenna switch modules. And so it will, like complicate the antenna form and the attached circuitry. So if we see the antenna for the 5G sub-6 gigahertz smartphone. So for this 5G sub-6 gigahertz, the major evolution in antenna are mainly driven by increase in the number of the bands and the quantity of the antennas. So the optimization of the architecture and its placement and layouts are their key to design of the performance. And the key consideration are, the MIMO technology, it become compulsory to support the high data rate transmission. Also this additional antenna to support this 5G sub-6 gigahertz band. And compared with the current, the 4G phone, we'll see the small change in terms of the electrical parameters that will be satisfied by the current material. So we don't see the no requirement of the new materials. And however, like with the increasing band and the antenna quantity within the similar phone size, it will affect the efficiency of the antenna, their isolation levels and envelope correlation coefficient and coexistence level with the systems, as well as with the over-the-air performance sustainability in the different user cases. Sorry, this slide is, So this is the antenna for this 5G millimeter wave smartphone. So here we will see the radical change in antenna design, because the phased array antenna is needed for, like for the beamforming, and to make it, the signal more directional towards the user equipment devices, and to compensate for high losses at this millimeter wave frequency and to improve the spatial coverage. Another is this antenna is integrated with RFIC inside the same package, and it will require the low loss material to limit the signal loss in high frequency environment, and to attain the better spatial coverage of the beamforming antennas and the complementary radiation pattern. So we will see, like the two kind of the antenna. So one will be the phased array, so patch antenna, and also another is the dipole. For example, the Yagi antenna will be, like implemented to cover, like the overall, the complete, the 3D coverage. And in terms of the number of the antenna in package, so minimum 3 is required to prevent the signal loss because of the obstruction by the hand or by metal or other substance. And another consideration, such as thermal management solution of AIP and or the phone case material type or gap between the AIP and the phone case, etc. They are also very, very crucial for the implementation of the antenna for 5G in the smartphone. In terms of the package, antenna in package, so it's like the three kind of the packaging solution is there. So one is this flip chip. So where we have like the RF transceiver IC is integrated in the same like the substrate, where we have the antenna is formed over there, and antenna integrates our elements are fabricated inside the substrate. So we have the patch, we have the patch antenna, and also the dipole antenna, and then this module is like put it over the board. Another, we have the fan out, where we have the RF chip. They are like integrated with the RDL, and so we have like the both side RDL. So top side we will have the patch, and the bottom side will act as the ground for them. But then like for this millimeter we need a certain height in there. So that is also very, very critical consideration. Another is is a kind of the package on package type, where the antenna is separately fabricated, and then like attached to the bottom package, which have the different the transceiver IC, RF ICs, and different components in a POP format over there. So we will see mainly this flip chip type or POP type that will be the mainly implemented currently, and then in the future we will see the fan out will also come into picture. So if we see like this antenna in package, so already like last year we have one phone, SS Gen Phone Pro. They have implemented this AIP for this WIGIG front-end module. So this module, they are integrated into this phone, and it has the two system which is linked by the coaxial connection. So both are the system in package, and they use this double-side molded packaging. And this module is developed by the Murata. And one is, like integrated to the main board, and other feature, the innovative antenna integrated into the PCB. So you can see over here, so the antenna, we have, this RFIC, that is, the flip chip bonded to this antenna substrate. So that is 8-layer SIP, and then the antenna is fabricated on this substrate, and then bottom layer is the 4-layer PCB substrate, and then like we have the thick copper pillar over here, connecting the both top and the bottom substrate over there. And it is developed by the subsidiary of the Qualcomm, Velocity, and it features up to 4 transceivers, and it controls up to 32 antenna, both the patch and the dipole. So we have the patch, we have the phased array, and for the dipole we have the Yagi type of antenna, and it is for the 60 gigahertz implementation, WIGIG implementation, and both have like very thin PCB substrate and embedded copper pillars. And it was the first integration of this millimeter wave device. And now, the Qualcomm, they have also have their different antenna in package modules, and for both, for this millimeter wave application in there. And the package size is around, like 40 millimeter square. And so overall, if we see the SIP, so it integrates around 20 antennas and RFIC, and also have the thermal management and the isolation solution in single package in there. Now we come to the substrate material for the millimeter application, especially where we have the single substrate that can support the antenna and also the this RFICs. So basically, the substrate can be divided into the core material or the dielectric RDL material, and the core can be the organic laminate, and it can be ceramic, and it can be glass. And then for the dielectric or build-up material, we have the prepay or the build-up film. And like for the high frequency signal transmission, there are different kind of losses. So we have the dielectric loss, and this like depend on the electrical properties of the material, and it can be reduced if you reduce the decay and DF of the material. And then we have the conductor loss, and this like mainly comes from the surface roughness and some kind of like discontinuity in the surface. And if we have very good adhesion between the dielectric and the conductor and the plating smoothness, so this kind of losses can be can be reduced. That's why I think one of the big advantage of this fan out over the flip chip is that it can reduce this kind of the conductor loss. And then we have the radiation loss, and it's mainly depend on the design and structure of condition. So like, for example, the strip line kind of the circuit, it exhibits, like no radiation loss, whereas the microstrip and the coplanar waveguide, it are prone to, like the radiation loss at the millimeter wave frequency. So there are, like the three basic materials. So the laminate and the glass and the ceramic. So if we benchmark these various substrate materials for the different criteria, so like they are, the multi-layer capability, electrical properties, and conductor processing capability, like forming, the line space in there, and surface roughness, thinness, size, cost, and material supply chain. So overall, like in terms of the various properties, so glass, they take a lot of, the requirement, but the supply chain, in terms of the supply chain, is still not ready. And also for the packaging companies, they have not so much experience with the glass. So even though glass has very good properties, but still it takes time to supply chain to come into place. So overall, if we see the implementation of there, so organic laminate, it will be the main material already implemented. So it will continue to be implemented for this 5G 6 gigahertz, and also for the 5G millimeter wave. But we will see also some kind of ceramic limited adoption. And the further, like if you go to more, advanced millimeter wave, and then we will see the ceramic and the glass, they will become one of the solution over there. In terms of this RF ecosystem complexity, if you see this front-end ecosystem, so we have at the module stage, we have only the 5 suppliers who supply these front modules. So we have the Broadcom and Murata, Skyworks, Corvo, and the Qualcomm TDK now merged over there. So it's 5 players. And then if you see the different components like switch, filters, and power amplifiers and tuners, all these. So we have the different, the companies, and then there are quite some companies in this filter IP design. And then we have the different OSATs over there, and the modem. So we have different companies like Qualcomm, Samsung, Intel. They are in the modem, and Intel recently exited yesterday. The news has come. They exited the modem business for the cell phone, but they will be for the PC servers, and also for the infrastructure. Overall, to summarize, so total packaging market will grow at like 11% to reach around 3.3 billion market. And so for 4G LTE, they use the multi-die system in package for front-end module, as well as the filter banks and diversity receive modules. And so currently, if you see in general 4G LTE, they front-end module, they compromise 10 to 15 dies, utilize the flip chip. So in terms of the interconnect, we will see more and more like interconnect power amplifier. It will completely move to the copper pillar in there, and we will see more like fine line space. And for this 5G sub 6 gigahertz, we will see the more like double-sided flip chip package with similar bill of materials, incremental innovation. It is the 5G millimeter wave where we need the really disruptive innovation. Antenna technology in placement, it is one of the most critical challenges for semiconductor system. So that is very critical. Another thing, fielding and molding, all these are very, very important. So with this, I conclude my presentation. So thanks for your attention, and the material for this presentation comes from a different report. We recently published this advanced RF system in package and status of the advanced packaging 2018 and the fan-out packaging 2019. Okay, thank you.
Thanks a lot, Santosh, for this interesting presentation. We will now going to wrap up with a Q&A session. As we are a bit late behind schedule, we'll have only the time for one question. So, Santosh, what are the chances for fan-out WLP and PLP adoption for RF SIP, including antenna in package?
So as I mentioned before, so in terms of the technology and benefits, those are very, very good technology. But still, I think the cost is one of the big barriers. And you know, like since for this double side, you know, keeping of the components or also antenna integration, we need, you know, like the double side RDL over there. And that I think is mainly, you know, like the companies like Semco, they have, and TSMC also they have, but the OSATs, they have, you know, like still in the development. So it will take some time when the, you know, yield will be good and the cost will go down. Then I think it will be implemented. So I see, you know, like maybe around 2021, 2022, around that.
Thanks a lot, Santosh. So the webcast is ending. You will get in 24 hours an email that will include the recorded session. Feel free to share the presentation of Santosh to whom will benefit from this information that have been presented. And also, let me remind you that you can find all our analysis and report on our new website, i-micronews.com. So do not hesitate also to contact us if you have additional questions. You can find the contact on the last slide of the presentation. We'll be glad to answer you via email. Thanks a lot for joining us today, and have a good day. Bye-bye.
Bye. Thanks.